So let's have the first non-trivial slide. So let's think about what cohomology does for us in general. The first obvious thing about cohomology is that it gives you a homeomorphism invariant for spaces. So you've got CP2, you've got the 4-sphere, and you can tell them apart because they've got different cohomology rings, and you say, hurrah, that's nice. And that's a fairly limited application. The next thing we can do with it is that it's something that we have a whole bunch of rules for how to actually compute cohomology. So we've got Mayer-Vittora sequence, we've got a lot of different machines that if you know that one space is equal to another space plus a little bit, or two spaces are very, very similar, you can say, aha, this is the piece of the cohomology that measures the fact that there's an extra handle, or something like that. And then the third big nice thing is that it's functorial, that you don't just study one space at a time. You take two spaces, and if you've got a map between the two spaces, you've got a pullback operation on the cohomology groups, and you get a tremendous amount of mileage out of that. And the fourth is that you could understand other things in terms of cohomology, that it's not just, okay, here is the cohomology of the space. It's, okay, we want to understand vector bundles over a space. So we figure out what their characteristic classes are, and those live in the cohomology ring. So that once you understand cohomology, that gives you the tools to do a whole bunch of other stuff with algebraic topology. So let's go to the next slide. And let's see where things stand in terms of tiling cohomology. So the first thing is in pretty good shape. So we've got a homeomorphism variant, and we can play lots of games to try to tell different tiling spaces apart using cohomology. And we've got just the check cohomology, and then we have variants on that, like the augmented cohomology that Bard and Diamond invented a couple of years back. And there are a lot of homeomorphism variants. But then when we start to do the other things, it's not in such good shape. We really don't have any cut and paste rules. That in most cases, the only way that we know how to compute the cohomology of a space is by using some sort of inverse limit construction. And what we can do cut and paste on the approximates, and sometimes that is good enough. But we don't really have any cut and paste rules for tiling spaces themselves, and that's partly because doing cut and paste is hard. You usually are dealing with translation invariant things, and it's a minimal dynamical system. So if you have a translation invariant open set, it's everything. So there aren't logical things to do cut and paste with. And then, as far as I can tell, almost nobody has really looked at using the functorial properties of cohomology. You've got the cohomology of one space or of another space, but you don't know what it means to pull back cohomology. It's partly that we don't have very good representatives. We can represent things with check classes, and what the check is cohomology. Nobody really plays around with check classes. And you can play with pattern equivariant cohomology, and those are very nice. But even there, if you've got a map between two tiling spaces, they're not always local maps. And so the pullback of a pattern equivariant function may not be pattern equivariant. And so you have a hard time understanding what pullbacks really mean, and so people really haven't done anything with pairs of spaces. And that, it's 2 and 3 that I really want to talk about today, trying to get a handle on that. And then the last thing, we've made some progress, but not enough. That we do know how to use cohomology for a few other things, like we've got the Gap Labeling Theorem. That was the first great use of cohomology, although you could say it's more K-theory than cohomology. And we know how to use the first cohomology to parameterize deformations, and we know how to use the top cohomology to tell us things about possible measures on the space. So it's all of the stuff that Jean-Marc Cambato is doing with his collaborators, and Kirchhoff rules and stuff like that. And on the dual side, the top cohomology tells you something about the convergence to the Aperiodic limit. Something I call exact regularity. But that's not nearly as good as the situation that we have for ordinary cohomology, and where instead of having 4 great pillars, we've got 1.5, and that's just not good enough. regular cohomology work? Relative cohomology. The main tool we have for connecting two spaces when we do ordinary cohomology is relative cohomology. And it's based on the idea that if you've got one space sitting inside of another, it has to be an inclusion for this to work. You have x as part of y, and then you define the relative chain to be the chains in y mod the inclusion of the chains in x. And you get this nice short exact sequence of chain complexes. And then we all know the snake lemma, that once you have a short exact sequence of chain complexes, you get this long exact sequence of cohomology, and then you're off and running. And you do all the things that you teach beginning graduate students about homology, and you can dualize everything and get, say, relative cochain complexes, or dual to the relative chains, and that's cochains on y that vanish on x, and you can write down the analogous short exact sequence of cochain complexes, and you can apply the snake lemma to that, and you get a long exact sequence of relative cohomology. Okay, let's move on. And the main tool that we use for doing stuff with relative homology or cohomology is excision. That if you've got a set inside of x whose closure is in the interior of x, then you can just remove it. You can just say it doesn't exist, and if we're talking about the relative cohomology of y relative to x, it's the same as the relative cohomology of y minus a relative to x minus a. And so the way to think about that is, well, first of all, if y is x plus extra pieces, all we really care about are the extra pieces and how they're attached to x. But it also means that if you think about the map from x to y, the inclusion map, it's one-to-one everywhere. But there are places where it's not onto. There are places in y that don't get hit. It's really the places where the map fails to be onto that tells you everything about the relative homology or the relative cohomology. The problem is when we're dealing with maps between maps on tiling spaces, you never have injective maps. They're always surjective, because you always, or certainly if you deal with factor maps, you take the image of a point, well, then you get the image of its entire orbit, and the orbit is dense so that you get everything. So you never have inclusions of one tiling space in another. You have factor maps which are surjections instead of injections. So the ordinary machinery of relative homology doesn't work. Now you can make things work using mapping cylinders. The homotopy theorists will tell you that every map is an inclusion if you think of it right. That works, but it's a very unnatural construction. All the things you like to think about for tiling spaces, they're hard to define. So instead, let's just act directly. Go to the next slide. Let's suppose we got a map between spaces, and these spaces, at this stage of the game, you could think of them as tiling spaces, or you can think of them as just ordinary CW complexes, just anything. You've got a quotient map from x to y. So it's onto, and let's suppose the pullback on cochains is injected. But this is what happens for tiling spaces. So examples of things where this works would be, say, covering spaces or branched covers. Any time that you can write, if you have a situation that every chain on x can be obtained from every chain on y can be obtained from a chain on x. If you've got that situation, then the pullback will tell you that every cochain, every non-trivial cochain on y will pull back to a non-trivial cochain on x. So for all these classes of maps, you've got this nice inclusion of the cochains of y into the cochains of x. So we'll define the analog of relative cochains is going to be these what we call quotient cochains. So the quotient cochains of x relative to y are going to be the cochains in x mod the pullback of the cochains of y. And now we just follow the same reasoning that we use for relative homology. We've got a short exact sequence. 0 goes to C star of y, goes to C star of x, goes to the relative guys, goes to 0. And then we just drag out the snake lemma. and we've got ourselves a long exact sequence of cohomology groups that if we can, and now, F star maps hk of y to hk of x, and we've got this relative cohomology group, which is just the exact relative cochains, the exact quotient cochains. They keep saying relative when I mean quotient. The exact quotient cochains mod d of the quotient cochains. And it ties together the two things. Okay, so let's move on to the next. So let's do the very simplest example I can think of, which is just you take a circle which you think of as being two vertices and two edges, and you identify the two edges, and lo and behold, you get an interval. That's a typical thing, and let's not use singular where there are infinitely many cochains out of every time. Let's just use cellular cochains. So there's only one cochain on y, and there are only two one cochains on x. And the quotient is just going to be, C1 of x is going to be generated by the duals to b and c, but the pullback of the dual to a is the dual to b plus the dual to c, and I'm using prime to denote duals. So this f star of a prime is b prime plus b prime, we just say b prime plus c prime is 0. In other words, b prime is equal to minus c prime, and we've got the first cochain group is just z. The zeroth cochain group is trivial because p and q just pull back to p and q, and so the complex is trivial, and you just have h1 is z. The quotient h1 is z, and the quotient h0 is nothing. And the quotient h1 just tells you how much extra topology you're getting from the addition, from the fact that what had been one edge gets split into two edges. Move on to the next example, which is only slightly more complicated, which is a figure 8 turning into a circle, where you just identify the two loops of the figure 8. And there you have the same thing, that if you call the edge of the circle E, that again, the relative cochain, right, the quotient cochain, you have C1 is just Z, C1 of x is Z squared, the pullback of C1 of y is Z, the quotient of the two is Z, so you have the relative C1 is Z, the relative C0 is nothing, so the relative H1 is Z, and the generator of that is, you could either take the generator to be A prime, and A prime is minus B prime, because A prime plus B prime is a pullback. Okay, so those were two pretty darn trivial examples, and you're probably wanting something that has something to do with tiling spaces. So let's move on to the next slide, which has to do with tiling spaces. So what I want to look at is the period doubling substitution. Period doubling substitution, A goes to BA and B goes to AA. And like every substitution of constant length, it's got a natural map to a solenoid. The natural map just keeps track of where you are within a tile, where you are within a group of 2, where you are within a group of 4, where you are within a group of 8, without worrying about which type of group of 1, 2, 4, 8, or whatever. So the way you construct the period doubling space is if you use barge diamond collaring. You construct it as the inverse limit of this complex, which has two long loops, one of which represents most of A, and one of which represents most of B. And then you have these short edges that represent the possible transitions. Since an A can be followed by an A or a B, you have these two edges, one going from A to A and one going from A to B. The B can be followed by an A, but a B can never be followed by a B. So that explains sort of the edges in the middle of what I call gamma PD. And if you look at that, well, that's homotopy equivalent to a figure 8. And meanwhile, the dyadic solenoid is just the inverse limit of a circle. So this relative cohomology is just the limit of the last example we did. The last example we did probably looked pretty trivial. but this is the same thing. So we've got a z in dimension 1, we've got nothing in dimension 0, and that's at the level of a finite approximant, and then you take limits. And you say, oh, the generator was A prime. How does A prime behave under substitution? Well, since an A appears twice in an A supertile, once in an A supertile and twice in a B supertile, substitution takes A prime to A prime plus 2B prime. But we said that A prime plus B prime was 0, so A prime plus 2B prime is minus A prime. So the effect of substitution is just to multiply this by -1 every time. So the quotient cohomology of the period doubling to the dyadic solenoid is just z in dimension 1 and nothing in dimension 0. Okay? And then if you go back, you say, oh, well, we know what the cohomology of the dyadic solenoid is. It's z of a half in dimension 1. And you do the long exact sequence, and you say that that means that the first cohomology of the period doubling space must be z of a half plus z. And now you don't just have the answer that it's z of a half plus z. We all knew that it was z of a half plus z. I mean, that's an old standard chestnut that we know how to calculate by variety means. But this sort of tells you what each term means. The z of a half is the part that it inherits from the dyadic solenoid. That's just measuring the two-adic structure. And then the z is measuring the fact that the difference between A and B tiles. And it can be represented by A prime or B prime or A prime minus B prime. And so now you know what the different terms in the first cohomology of the period doubling space mean. So let's go on to the next slide. Now, another way to look at doubling relative... Is there a question? Yeah? Go ahead. Oh, okay. Oh, okay. Gesundheit. Okay, so, something's weird with the sound. But, are you hearing me okay? Okay. Now, the thing about the period doubling being a z in addition to the dyadic solenoid shouldn't be too surprising, because the map from the period doubling space to the dyadic solenoid is one-to-one almost everywhere. If you take the period doubling space and you take two asymptotic orbits, you know, the period doubling sequence you can get by saying every other letter has to be an A. Then of what remains, every other letter has to be a B. Then of what remains, every other letter has to be an A. Then of what remains, every other letter has to be a B. And you got this. You could do this and wind up with one hole in the middle after you're all done that can be either an A or a B. That gives you two orbits that are asymptotic in both directions. And those orbits are the only place where the map from the dyadic solenoid, from period doubling to the dyadic solenoid, fails to be one-to-one. So what's sort of happening here is you've got these two asymptotic orbits being mapped to a single orbit. So you've got this bubble that's sort of joined at infinity, mapping to a line, or you could think of it as sort of a circle with two rays going off to infinity, mapping to a line. And of course, that was the first example we did. We saw that had quotient cohomology z in dimension 1. And if you want, but that's a hand wave. You know, we've essentially done is we said, forget the rest of the space, we care about these two orbits that get squished to one. How do we know we're allowed to forget the rest of the space? So we need to develop some more technical tools for dealing with this kind of quotient cohomology in order to make sense of this, suggestive but not convincing hand wave. So let's go to the next slide. So the first big theorem is excision. Now, excision directly on tiling spaces is hard to do, but let's state it in... So it's the same excision... Instead of looking at a place where things fail to... What you had for ordinary excision is if you had something sitting inside the small space, which sits inside of the big space, you can forget about it. Those are the points where the map was one-to-one and onto. and it was only the places where the map failed to be onto that mattered. Here we're going to do the reverse. We can throw away the points that are one-to-one and onto, and it's only the points where it fails to be one-to-one that matter. So if you've got X mapping to Y, and you've got a region in X, an open set that, its closure has to sit inside of X. Its closure has to be one-to-one on the closure. Then you can remove it, where you have to remove it from X and you have to remove its image from Y. And the way to do this is that what I said before about the existence of these definitions of the quotient cohomology. Quotient cohomology really isn't a new object. I said that you could make it work in terms of mapping cylinders and ordinary relative cohomology. There's a shift in dimension by one, and it's a little bit clumsy, but you can express it in terms of ordinary relative cohomology. So if you do that, and then you apply ordinary excision, and then you convert it back, then you get this excision theorem. So I'm not going to go through the details of that proof, but it's really piggybacking off of ordinary excision on the mapping cylinder. And that's this theorem. And now you might think, how are you ever going to get these open sets? Well, you can, if you're working on a level of approximants, you can usually find these open sets, and then you have to take limits. And using that, let's go to the next slide. You can prove the theorem that allows you to do things like the period doubling example. So we've got a factor map of tiling spaces, and let's suppose that the map is one-to-one everywhere except what I call this k-fold suspension of a lower dimensional tiling space. So in the case of the solenoid, the lower dimensional tiling space was just 2 points. That's a zero-dimensional tiling space, and that got mapped to 1 point. More generally, what we're interested in is a set of tilings that are asymptotic in all directions perpendicular to, that are asymptotic in all k directions. All directions in a k-dimensional space, and then in the n minus k-dimensional space, you can translate in that n minus k-dimensional directions. And the idea is that 2 points will get identified if and only if they're asymptotic when you move in the perpendicular directions. So that was what we had for the solenoid, where we had 2 points that if you translate very far in either direction, they come together. And another example would be the half-hex tiling. So that in the half-hex tiling, it maps to the two-dimensional dyadic solenoid, except that there are 3 different tilings that are all asymptotic in all directions. So that would be a double suspension of 3 points mapping to 1 point. So what this theorem tells you is that if you take 3 points mapping to 1 point, well, the quotient cohomology is just z squared in dimension 0. Since it's a double suspension, you get z squared in dimension 2. So this allows you to say the cohomology of the half-hex has to be essentially a z squared in dimension 2 more than the cohomology of the dyadic solenoid. So what you've got is, the cohomology of the dyadic solenoid is z of a quarter in dimension 2, and z of a half squared in dimension 1, and z in dimension 0. And then the quotient cohomology is z squared in dimension 2. And you put it together and you say that the half-hex has to have z squared plus z of a quarter in dimension 2. And again, the z of a quarter just reflects the hierarchical structure, while the z squared comes from telling the different kinds of tiles apart, and comes from this relative business. Okay, let's move on to the next. And now we've got what I think is a more interesting example, one that we all know and love, and that Robbie wrote a lot about quite a while back, about the magical fact that the chair tiling looks kind of like the dyadic solenoid in 2 dimensions, but it doesn't map 1-to-1 to the dyadic solenoid. It only maps almost everywhere 1-to-1, and it's got these spaces where it maps 2-to-1, and then and then it's 5-to-1 over a single orbit. And you want to say, can we figure out the difference between the cohomology of the chair and the cohomology of the dyadic solenoid in terms of the set where it's 2 to 1, in terms of the set where it's 5 to 1, and I wouldn't be bringing up this example if we couldn't do it. So here's how we do the game. The 2 to 1 set is actually sort of like an X. You take certain tilings, and if you translate them in the northeast to southwest direction and take limits, or if you translate them in the northwest to southeast direction and take limits, then you get 2 to 1. But that's not a tiling subspace. There's no particular direction. So we're going to do things in 2 stages. I'm going to define a tiling space omega HC. HC stands for half chair, where omega HC over the dyadic solenoid is only going to see things in the northeast to southwest direction, and chair over the half chair is only going to see things in the northwest to southeast direction. And we can do each step using the machinery that I've laid out so far, and then you put it all together and you get the chair over the solenoid. So what do I mean by the solenoid? Well, the solenoid we'll think of as an inverse limit of what's actually a periodic tiling, but we're going to imagine that we can keep track of the hierarchical structure. And the substitution is we've got 2 kinds of tiles. One where a line is running with slope 1, one where a line is running with slope -1, and both of them substitute to 4 squares with the lines running out from the center. Now, let's go to the next slide. Now, here are the substitutions for the half chair and for the chair. If you look at the bottom half of the slide, you see the usual substitution for the chair in terms of arrows. Now, if you look at the top half, you just say, let's just erase the heads of all of the arrows that are pointing northwest or southeast. You know, since the arrows that were pointing, if you look at what happens to a northwest arrow or to a southeast arrow, the only differences in their substitutions is that some arrows wind up pointing northwest instead of southeast. So you can erase all the northwest to southeast arrows and just, you keep track of northeast, southwest, and the other way. And so you get the substitution on the top half of the page. And that's going to be the half chair substitution. Okay, next slide. So now let's look at what happens when you go from the chair to the half chair. Now the thing about the chair is if I give you a big super tile, if I have a gigantic super tile and it was running northwest, or if it's running southeast, those super tiles wind up being identical except on that diagonal. So the only places where you cannot reconstruct whether the arrows should be pointing northwest or southeast is if you've, well, one example is if you have 4 infinite order super tiles all meeting at the origin. If that happens, then you don't know whether, well, it could be that along the anti-main diagonal, the slope -1, that they're all pointing northwest, or it could be that they're all pointing southeast. You can't tell the difference. But that's just a single orbit. If you then translate in the northwest direction and take limits, well, then you get more than a single orbit, you get an entire solenoid. And if you translate a finite distance in the northeast or southwest direction, that's also okay. So what this winds up being is a suspension of a map that takes 2 solenoids and identifies them. So what's the quotient cohomology of 2 solenoids mapping to 1 solenoid? Well, that's just the cohomology of 1 solenoid, which is z½ in dimension 1 and z in dimension 0. So since we suspended it once, we get z½ in dimension 2 and z in dimension 1. So now we know what is the cohomology of the half chair. It picks up the z½ in dimension 2, it picks up a z in dimension 1, and otherwise it looks like the cohomology of the solenoid. Now let's go to the next slide. Sorry, I said that was the half chair. Sorry, that's not the cohomology cohomology of the half chair. That was chair relative to half chair. Half chair relative to solenoid is a little bit trickier. Because, again, you've got the picture of what happens if there are 4 infinite order supertiles that meet in the center. And you want to figure out which way are the northeast and southwest arrows pointing. And you could have both of the, you could have 2 supertiles both pointing northwest, or you could have northeast, 2 pointing southwest. You could have the supertiles pointing into the center, or you could have the supertiles pointing out of the center. And then you can take translates of them in the northeast direction and take limits. But of course, if you take a translate in the northeast direction and then take a limit, then the first and the third pictures will look the same. And the second and the fourth pictures will look the same. And if you translate infinitely far in the southwest direction, then the first and the fourth will look the same, and the second and third will look the same. So what you've actually got is a situation where you've got these 2 solenoids, which you can think of as being the orbit closures of the first and the second. And then the third and the fourth serve to to link the 2 solenoids. So we've got a picture that looks like 2 solenoids with 2 orbits that connect the 2 solenoids as an X. And that maps to a single solenoid. And if you figure out what is the relative cohomology of that, well, suppose you didn't have the 2 X's in the middle. There's the 2 things in the middle that link them. Then it would be just like what I talked about before. You'd have a z of a half in dimension 1 and a z in dimension 0. If you have one thing linking them, then you don't get anything in dimension 0. If both are connected, you just get a z of a half in dimension 1. If you have both X's, both things linking, then you get a z and a z plus z of a half in dimension 1 and nothing in dimension 0. But it's a suspension, so you get that in dimension 2. So the upshot is that you get H2 of the half chair relative to the solenoid. Let me write this down. Could you give me a Kleenex for erasing? Getting my lab assistant here. So can you see the board? Okay, so we've got is the cohomology of the half chair relative to the solenoid is in dimension 2. We wind up with z of a half plus z. In dimension 1, you get nothing. In dimension 0, you get nothing. If you take the cohomology of the chair relative to the half chair, you wind up with a z of a half in dimension 2, a z in dimension 1, and a 0 in dimension 0. Okay? Now, we somehow have to combine these two to get the cohomology of the chair relative to the solenoid. And when you combine the two, the remarkable thing is that this z and this z almost cancel. It's not just a direct sum. You actually get something interesting happening. And you wind up with a z of a half squared, because you get both of these, plus z mod 3. And you get nothing in H1 or H1 or H0. So it's kind of weird. You put it together and you get torsion. So what does this torsion mean? And the torsion, let's go to the next slide. So the torsion, it's not that the cohomology of the chair has torsion. The cohomology of the chair is z of a quarter plus z of a half squared. That's the top cohomology. But it's not really z of a quarter times z of, plus z of a half squared, because if you take the generator of z of a quarter in the cohomology of the solenoid and you pull it back, what's that generator? Well, it's the thing that counts squares. But you know that if you think of the chair tiling as actually being made of chairs, there's a cohomology class in the chair tiling there's a piece of the chair tiling that will not count squares, but count chairs. That will evaluate, say, 1 on the base of a chair and evaluate to 0 on the wings. And then 1 on the base of the chair and 0 on the wings. And 1 on the base of the chair and 0 on the wings. That's a perfectly good pattern equivariant code chain on the chair space. It's not the pullback of the generator of the cohomology of the solenoid. 3 times this is the pullback of the generator. So that's the z of a third. If you take this group mod the pullback of the cohomology of the solenoid, you get z of a third, because this is non-trivial, but 3 times it is in the pullback. So that's the torsion. It's not torsion in absolute cohomology, but it is torsion in the quotient cohomology. So that's almost as far as I want to go. Let's go to the last slide. And I just want to finish off with a possible application of all this machinery. We've got a lot of theorems that relate substitution tilings to finite matching rule tilings. This was the stuff that Shahar Moses did way back when for substitution subshifts of constant length, and then Charles Radin did it for the pinwheel, and then Chaim Goodman Strauss generalized it the farthest. And basically it says if you've got a substitution tiling, then there exists another tiling space given by local matching rules that maps almost one-to-one onto the substitution tiling space. And you can say exactly where that map fails to be one-to-one. It fails to be one-to-one when you have an infinite order supertile that takes up half the plane and another infinite order supertile that takes up the other half of the plane, and then there's some ambiguities about what can appear on the boundary of those 2 infinite order supertiles. Well, that's exactly the kind of suspensions that we know how to deal with our machinery. Or sometimes you have 3 or 4 infinite order supertiles meeting at a vertex, and then you're going to have a double suspension. Or sometimes you'll have this piece and that piece and something in the middle, and it'll be sort of like the chair mapping to the solenoid, where you've got different pieces where you have to figure out how to do it in multiple steps. But I think that this whole game will give us a tool for taking what we had known about substitution tilings and then saying, you know what, here's something that looks like a tiling space that we know and love, but it has this extra feature, and here's how much cohomology comes from that extra feature. Fold it in. Maybe there's an extension problem, maybe there isn't, but combine it all to get the cohomology of a more complicated space in terms of the cohomology of a simpler space and the way that the 2 spaces are related, which, after all, is what cohomology is good for. And with that, I'll stop.